Okay, welcome everybody to this talk. It's a pleasure for me to introduce Frantisek Duris.
Yes, Duris.
Duris.
Yeah.
Sorry. Well, he's right now here at the IAC. He has been for 3 months,
Yeah.
more or less, in the framework of an Erasmus Plus project between the IAC and the Comenius University. He has been working here with Javier Licandro and Marcel Popescu. Well, he did his PhD in a field completely different to astrophysics. In fact, he's a computer scientist. But well, he loves astronomy and he liked to do something related to astronomy, and he started working with Dr. Jura Todd in Comenius University, working in meteors and asteroids and that kind of stuff. And well, right now he's going to talk us about a little bit about software development for the analysis of meteor and asteroid data here at the IEC. Thank you.
Okay, thank you for the introduction. So, as Jorge said, I'm an Erasmus Plus student, been here for 2.5 months. So for now, I'm leaving this week. So I came here to learn something new, mostly because in Slovakia I work with meteors and specifically the data reduction, developing a software for our observations. But here there is no meteor group, so I joined the next best thing, which is asteroid group, and so I learned a lot about data reduction in asteroids and stuff around this, because here they take images, in Slovakia we take videos, so it's a little bit different. So I will talk about this. I will talk about my work in Slovakia a little bit, because the instrument we have, AMOS, is installed also here on Canary Islands, and I will mention the software that I develop, and also I will later talk about work that I did here with respect to the meteors and mostly the photometric data reduction. So, in Slovakia, I work with Juraj Todd and Lajos Kornos. Maybe many people know Juraj Todd because he's quite popular in media, especially in Slovakia. And I develop a software called Meteorium. Before I talk about our instrument, I will briefly mention what we study. So we study meteors, which are luminous events of meteoroids passing through the atmosphere. Meteoroids are smaller versions of asteroids, up to 1 meter in size. And they are mostly fragments from comets or asteroids that originated through the impacts or comets getting closer to the sun and evaporating some of the material. What we learn is dynamical properties of the meteoroids, their chemical or physical composition, and also by studying the meteoroids we can learn something about their parent objects. Meteoroids seldom come alone, they often are in streams. It takes just a couple of revolutions around the sun to disperse the stuff around the whole orbit. As I said, they usually originate from the comets or from the asteroids through breakups or impacts or getting closer to some bigger object like planets. And usually they produce quite a spectacular shows called meteor showers when Earth passes through the whole stream. So, our instrument is called AMOS, All-Sky Meteor Orbit System for the continuous observation of the meteors. It was designed and developed by mostly Juraj Todd, Pavel Zigo, and Kalmančok, but also many other people participated. It's an autonomous optical system that basically takes video of the sky. We are using the fisheye lens, so we can see the whole sky at once. The limiting magnitude for the stars is around 5, and for the moving objects, it's about 4. This depends mostly on the software that processes the video, for which we use the external company. And usually we take around 10,000 up to 20,000 observations per year on a single camera, but only 30 to 40% are simultaneous with its paired camera, as I will explain later. This is how it looks on the Teide Observatory in here in Canary Islands. During my visit, I actually performed some service and I cleaned up the optics because it was pretty dirty, and I was surprised that we can actually see anything through it anyway. So this is how it opens during the night. During the day it's closed, and it can observe during all phases of the moon and even with a partially cloudy sky. We just need enough stars to do the astrometry, and then it works fine. So how does it work? Is that we have at least 2 cameras. Each observes the meteor with a different plane of sight, and when the plane of sight intersects, they contain the meteor trajectory. So the distance between the cameras should be around 100 kilometers, more or less, and they need to observe the meteor simultaneously. Then we can actually calculate the trajectory, the orbit, and even the dark flight and the impact of the meteorite, which we can later find. So this is the fireball that was observed in Chile, and the meteorite was found in the desert, which is pretty easy because it's black on the yellow-brown. The purpose of our observation is to study the dynamical properties of the meteoroids, of the apparent bodies, also to examine their composition through the spectra. This is the image taken from Tenerife during the Geminids meteor shower. It's a composite image from the whole night. Then we study orbital elements, because with orbital elements we can determine what is the parent body, if the parent body is known, or by accumulating a large database of the observation, we can actually dig through the database and discover a new showers. AMOS is installed at 4 places around the world. There are 3 cameras in Slovakia, 2 cameras in Canary Islands on Teide Observatory in La Palma. Then we have 2 cameras in Chile and 2 cameras in Hawaii, which were installed in 2018, latest. And also we would like to have another 2 cameras in South Africa and Australia to cover basically the whole Earth. Then we can calculate, for example, the influx of material that comes from the meteoroid objects to the Earth, and the density of this flux. Also, the AMOS was part of the first airborne observation of the meteors for the Draconids 2011. So there were 2 planes flying around the northern part of the sky, around the Scandinavia, and they were on the top. Here you can see there is a window, and the AMOS was mounted and looked through the window. So this is basically about our instrument. It takes the video, and then we have the data processing that actually processes the video and gives us what we want. So part of the data processing routine is Meteor software, which is not yet complete fully, but in future it will be the main data reduction software for our data. It can do basically everything from astrometry, which currently we are still updating, to the atmospheric trajectory, then the velocity models, where we have impact coordinates, orbital elements, then we can calculate the photometric mass, estimate the errors, and visualize the results. It's for now, it's mostly used for the larger objects, where you can actually go case by case. But it can also run in like a whole folder of the data observation. What we do not do is process video, because there is quite difficult, but we have external company, Quant SRO, that produces this software for us. So about Meteorium, it's based on the Ceplecha paper, 1987. which basically, in this paper, he outlined the whole data processing routine to get from the astrometric position of the meteor points during the observation. So we have right ascension declination of each meteor point with its time, with coordinates of the station, and then you get the trajectory, then you get orbits, then you get velocity models, then you get dark flight. Everything is outlined in this paper, and basically the whole software was built around it. This is not the only paper we used. We also used other models to calculate the trajectory by Borovička, by Gural, but the whole idea originated to have something that was described in this paper so we can actually easily apply it to our data. It is built in Lazarus, object Pascal, and R. The R is used for the numerical simulation and the graphical output. The Lazarus is used for basically the graphical user interface. It's not a dead language, as many people think, the Pascal, but it was the only one I knew at the time I started working on this, so that's why it's in this language. Today I would probably choose a different one. So as I said, it runs for the single case or the whole folder, and it has a simple graphical user interface that you can actually click your data in and get the results with some parameterization. I briefly say something about the inputs and outputs. So basically what we take into input is either after astrometry, where you already have the right ascension, declination, or azimuth and zenith distance of each meteor object, of meteor observation. We have a video, so you can cut the videos into frames. So we have about 15 frames per second. And then we basically use this data. Or you can have the X and Y coordinates of the meteor observations in the image and do the whole astrometry before this. It doesn't really depend in which text format you have this information. It's easy to write the routine that will parse any format. Currently, we are using the data from Sonotako UFO Analyzer or metric data or our own input files from the Quant, which was developed for the video processing. As for the output, we have a text report that is easily readable by the astronomer, but we also produces a lot of graphs and tables for each observation, also from the simulation for the dark flight, where you actually see how the object flew through the atmosphere when it was not shining. So a couple of outputs can be seen here. So for example, on this, you can see the orbital elements or the visualization of the orbit of the object, which is in dashed line. Also, we have here a visualization of the velocity model. We can see that the deceleration along at the later part of the trajectory, and we have some Monte Carlo simulation results here. And we produce quite a lot of data, so we can actually see that if the object was processed correctly, and also a lot of information can be gathered from this kind of output. Okay, so this is basically the input-output of our software. Now I would like to talk a little bit more in detail about some maybe interesting parts of the software. So first, I would like to talk something about astrometry. Currently, we use the UFO analyzer from Sonotako to do the reduction. But the problem with our data is that it's all sky, meaning it goes through the fisheye lens. And fisheye lens has a lot of distortion, so it's very difficult to actually do the astrometry with tools like astrometry.net. Sonotako works, but he also, from the personal communication with our colleague, mentioned that it was not supposed to work for this kind of wide fields, so sometimes it does not give really a good results. Then there is a Borovička, or group around Borovička, who also have a fisheye lens, and they developed their own routine published in 1995, Red Sky, and it uses a 13 different reduction constant to actually correct this kind of distortion from the fisheye lens and get a better results. So the comparison of the results can be found in these two images. This is from the Sonotako. Basically, it shows the original stars as measured with their catalog stars, with their matched catalog stars. The shift is done by the correction of the distortion of the lens. It is multiplied by 50, so we can actually easily see the type of errors that we get. And this is from the all-sky Borovička procedure. So the mean error of both procedures is about the same, but we can see that there is there is more systematic error in this case than here. Sonata uses the polynomial to do the transformation. Borovichka uses other highly nonlinear functions to find the right transformation. So for our astrometry purposes, we are building on the Borovichka procedure, but we are using it as a subroutine, and we also try to change the internal parameters, several other internal parameters, to get a little bit of better results. So this is a work in progress, but we are getting a little bit better results than the Borovichka procedure itself, because we are calling it several times and trying to help it to get a better reduction constant. Okay. Then another interesting point maybe are the impact points. The equations are written in the Ceplecha paper for the single non-ablating body. So we are using the Runge-Kutta integration of these equations to get the trajectory. But the trajectory is quite strongly influenced by the weather of the around the object. So we download the data for each case automatically from the internet, the weather and the atmospheric model, and use that as well. For example, you can see that the trajectories are quite curved, which was caused by the different winds in different layers of the atmosphere. Then also another factor that influences the dark flight is the shape of the meteoroid object as well. Its size, its drag coefficient, which changes quite a lot with the different objects. So what we have is a meteorite that landed in Košice a few years ago. And one of our students actually did a 3D model of this object. And we are using the simulation of this model to actually calculate, okay, so what are the drag coefficients and intersection of cross-section of this object, so we can actually get more realistic results from the dark flight simulation. So far we have only one object like this scanned and used, but if it is easy to add new objects, when we found new meteorites, we can scan them and use this procedure as well to get actually more robust estimation of where the meteorite could land it. So this is, so far we have 8 points. We also include rotation of the object, either regular or random, and all of the for all of the drag coefficients and cross sections, we get a line, and we have a sort of a set of lines where the object would land it. We also do Monte Carlo simulation of errors, so we actually have an ellipse drawn around, but I could not make it work in my software to visualize it. So as a result, we get after the meteorite in Košice was found, we got closest to the real site of the meteorite, but that was probably because we actually used the object itself to simulate the cross section and the drag coefficient. For different objects, it will be different, but when we compile a large enough database of the scanned objects, then we can actually project not lines, but the whole area based on different sizes, different drag coefficient, different rotations where the object could have landed. And the final that I would like to mention about this software is the calculation of photometric mass. It's based on the paper by Koshny in 2017. But what I would like to mention is that usually when people calculate the photometric mass, they only take account this part of the equation, where you can see there is intensity, which is calculated from the observed magnitude. Then you have some constants, speed, and the change of the mass in time. And so mostly people use only this part of the equation. Since we observe the deceleration as well, especially for the larger objects, then this term is also quite contributing quite a lot. So we were looking for a solution how to get it inside. It is a differential equation, and we did not find any solution to this, so we decided to do the iterative process of finding the best solution. At first, we assume there is no deceleration and compute sort of an initial mass, and then in each subsequent iteration, we plug in the previous mass to this equation and get a better improvement. And what we observe for most of, or all of the cases, is that the convergence of the process is pretty quick, and it's quite different from the starting point. So this is a little bit better approximation of the luminous mass. Also, still the equations in the equations used here assume that there is only one body that goes down, and one body that is actually shining. When the meteorite breaks up, then it actually has a lot of bodies, and they shine a little bit more, and it's not taken into account in this equation. So this is sort of like a limit. Like, okay, it should be at least, at most this size, but maybe it was shining a little bit more than it was supposed to be due to the more number of the bodies. So this is like an upper limit of the mass. So these are the interesting parts of our software. We are still working on it, improving it, and trying to make it work better. Also, I would like to mention two interesting problems we were solving. One is that how to assign timing of the like absolute timing of the events, because you have two cameras at least, and each camera records the relative time. So the event started at the time 0, and there is a first frame which is 15 hundredths of a second, and second frame, second frame, second frame, and you have this from the two cameras. But to get a good model, for example, for the velocity, you need to have absolute timing of each point. And so we are trying to discover how to do this. Because what if you cannot be sure about the synchronization of the cameras? And also the cameras could start recording the event at the different parts. Some camera, they are apart a little bit, and also could be a cloudy sky a little bit, or for some other reason, one camera sees the whole event and the other only the half. So we are trying to figure out how to put these times together. And so what we come up with as a solution is that so we plot the observation of each meteorite of each meteor point on the time and the distance along the common trajectory. Because for the common trajectory, you don't really need time. The lines of the plane of sight from one station, the plane of sight from the other station, they intersect and create a trajectory of the common trajectory of the meteor. And then you can actually see that, okay, the point from this station was here, the point from this station was here, and so on. So you know the distance of the points along the trajectory. You don't need time for that. And then you have so this is on this axis. And then you have on this axis the time. So each point, since the camera records only relative time, the points are above each other, because the first point is the time 0, the second point is 0 plus delta t, and so on. And but we want to merge them together, so we know that okay. But what is what is the timing of this point with respect to the other station? So what we did was we only take one station at first, for example, the red one, and we use a linear model of the distance of the point along the trajectory. There is a deviation from the linear model at the end because the object decelerates. So it goes less and less and less and less along the trajectory in the next time. But we took a robust linear model that can basically only fit the first part of the points that are linear, and then we calculated the distance of the blue points from this model and take a median of this distance. And then we actually add to this blue point, to every blue point, the median of the distance. So now, I don't know if it's visible on here, but we can see that the blue points now are much better fitted with the red points. So this gives us like a time delay between the recordings of the first station and the second station, and then we can use the absolute time of the first station and plus the relative time for each point now that we have it. So this was one interesting problem we solved. The other interesting problem is that how to calculate the uncertainties of our computations if you have only one observation. You have only one trajectory, but you want to know the error of this trajectory. or you have only one velocity model, but you want to know the error of this velocity model. So what we did is that, okay, so we have the two planes of sight, they intersect, and you project each point on the common trajectory. And then you can calculate actually the deviation of each observations from this common trajectory, which can be seen here. So we used this as a seed for the Monte Carlo simulation. But it turned out that the errors from this kind of simulation are too small because, well, you have a long line, a lot of points along it, and even if you generate the points around this line, then you cannot actually move the line much because the restriction, because it's too long, and you have many points around, so the line is difficult to wiggle, even if the errors are quite large, because it's really difficult to wiggle a line in sort of a tunnel like this. So what we did is that we also took into account the astrometry errors, and they cause a systematic error. So for each Monte Carlo simulation we generated from this distribution, we also shifted all of the set of points in some direction by some random amount based on the error of the astrometry. So we have a sort of two-way simulation or two-way generation of the Monte Carlo points. First you disperse them around the general trajectory, and then you shift actually all of the points in one set by some amount to take into account that the astrometry could have been wrong a little bit, and all of the the coordinates of each point of the meteor should be shifted a little bit to either direction. And this gave us a lot more robust estimation, basically bigger, reasonably bigger errors in our data. Okay, so these were maybe two interesting points. We struggled with this quite a lot. We talked with our Czech colleagues quite a lot about this because they warned us that our estimation of error is very small and it's not realistic. So we were trying to figure out, like, okay, so what to do about this. As for the future, this is about mostly dynamics of the meteor, but I would like to create a sort of meteorite, meteoroid workbench where you can also do the spectra, composition analysis, classification, sort of everything you can get from our data, and have it under one software package. Also improve the astrometric precision or several procedures, because in this community a lot of people do the computation in their own way, for example the errors, and it's hard to compare between different groups because everyone come up with their own way to calculate the errors, and then they are hard to compare. So also we would like to cooperate more with other people and actually agree on what is the best solution to this kind of problem. And also, since we collect quite a lot of data, we can actually start to build a big database and then try to mine in the database for some interesting information. The second interesting thing is that I would like to use the Meteorum as a web service, similar to astrometry.net, where you can upload your data and then we will give you back the results. So hopefully in not so distant future we can have this running. There is a little bit of problem with the format of the data, or because some cameras are all sky, some cameras use only the narrower field of view, so the astrometry procedure will be different. But through the collaboration with that group, we can actually build a module of the software that can process this kind of data as well. So this is for the future of our software. Hopefully not too distant. So much for my work in Slovakia, and now I would like to talk a little bit what I did here. Here I was working with Marco Piscu sitting here and Javier Licandro as a supervisor. We were basically processing the asteroid data they observed with the photometry pipeline. So the instrument we used is Muscat 2, mounted on the Telescopio Carlos Sanchez on Teide Observatory, and basically the most important thing is that it's a simultaneous 4-color camera. So at each observation it takes 4 images in different bands. The images are not perfectly aligned, but they are close. So I tried to make a video, but I failed. when you stack them, they are not perfectly pixel by pixel aligned, but they are not too far off. But this is important to remember because I will use this information later in the talk. So this is instrument we were working with, and we were using a photometry pipeline software by Michael Mommert, which was published a year ago. And basically, it's an excellent Python package that you give it an image, and it will give you the calibrated photometry of your object. So it will find the stars, it will do the astrometric solution, it will download the photometry catalogs, and then it will calibrate the instrumental magnitudes of your target and give you the real calibrated magnitude of your object. It is quick, it is quite easy to install, it is pretty accurate, but the problem is that it does not work always. So what we were doing with Marshall is basically building a software above this pipeline to make it work for the most or all of our data. So briefly, how this photometry pipeline, the original one, works. So it has three important steps. First is image registration, where it calculates the astrometric solution of the image, so you know which stars are which points, and then for this, it uses the source extraction routine, which is based on the Sextractor, pretty good software that is been around for a while. And for the image registration, it uses the SCAMP software package. Once the registration is done, it calculates the optimal photometry, instrumental photometry. It is aperture photometry, so it takes a circle around each object, and then all the pixels in this object are taken into account for the instrumental photometry. It is a question of how big this circle should be. The pipeline takes 20 different circles, and based on its internal metrics, it picks the most optimal one. It can be based either on the target or on the background stars, or both of them. And once we have instrumental magnitudes, it uses the calibration through the various catalogs you can download from the internet to get the real calibrated magnitude of the object we are interested in. So this is the process in the nutshell. But like I said, it does not always work. Sometimes there is noise, artifact, trails in the images, there is too little stars, or the initial coordinates where the telescope is pointing is in the FITS file header. It's far off from the real solution, so the image registration fails. This is the basically the only problem we experienced is that the registration fails, and then we cannot continue. So what we looked for is a solution to this problem that is general, automatic, and simple, because we wanted to apply to all of our data, and we don't want to go picture by picture. Okay, what was wrong with this one? What was wrong with this one? And so on. We want a general solution. So for that, we built a software called PYPER, which is a Python script built above this photometric pipeline. Basically, it is a set of tricks to make the photometric pipeline work, as I will talk about it later. Note that we using the modified photometric pipeline because for some of our trick works, we need to modify the pipeline in a way that it can pass a little bit more parameters to the Sextractor and the SCAMP software that it uses. So if you download the photometry pipeline from the internet right now, it will not work with our software. I'm communicating with the author to change this a little bit to include my options in his script as well. He told me that he will look into it, but he has not replied for a week now. So I will see what it will come out. So as I said, the photometric pipeline not always work, but we found that a very simple solution is to run the pipeline twice or more times, because during the computation, the SCAMP creates a head file containing the FITS header and some other information that it computed, and the Sextractor can sometimes read this information to get the better results. But since the Sextractor is run before SCAMP, this kind of interaction could not come in the photometric pipeline originally. So, but if you run it twice, the file is already there. The Sextractor can use the SCAMP file, and actually it works quite a lot of time. And in fact, Mommert agrees the author, because he added a new option in his photometry pipeline to run the pipeline actually twice for the more successful registration. So this was a pretty simple solution and pretty successful. What we found that there are two variables describing how good the astrometric solution is, and we noticed that with the multiple runs of the pipeline, these sort of variables increase, meaning the trustworthiness of the astrometric solution is better. But what we observed that the magnitudes and the coordinates of our target does not really change. So it does not really matter if the registration ended here or here, because it has no effect on the target. So this was a pretty simple solution, and we discovered that it's because of these head files, and it works. But it does not work always, right? So what we used next is that, okay, so we have Musca data, we have 4 images for each observation. So if one of the filters was successful, but the other not, so maybe the head file of the successful filter can help us actually to achieve the better registration, and in fact it does. Sometimes, but actually quite a lot. So what we do is just we take the head file of a successfully registered filter, copy it to the head file of replace the head file of the failed filter with the new one, and run the pipeline again. And it actually works quite well. It does not work always, because for one thing the images are not perfectly aligned, and also there is a different distortion for each camera. So it doesn't work always, but quite often. Also the problem is that what if none of the filters are registered, right? So what to do when there is no registered filter, or the one does not help? Is that okay, but we also have a series of images. So we took a lot of images before and after. So let's look at the successfully registered files that come before in the same filter. So for example, in the previous file could have been registered fine. So we take its head file and run the registration again for the problematic case. And again, it works quite a lot. Okay. So we have 6.5 million light sources identified in our images, which contain mostly noise, but may contain also something interesting. So after this, I'm planning to actually look through this database and check for the variable stars and check what other sources were identified apart from the noise. And yes, so basically that concludes my talk. So thank you for your attention. If you have questions.
Thank you for the interesting talk. Okay, we have time for questions. Questions, anyone?
Okay, thank you very much. I have several questions have arisen to me. Listen, you mainly from the Slovakian part, talking about the astronomy, the astrometry, and so on. So, the first thing I was thinking about is the speed of the meteorites relative to the Earth is high enough to take into account relativistic effects in the time contraction and so on. This, I thought that because you mentioned that it is an important part to take the exact time of the observations and so on. This is one question. Well, this is one question. The other one is, in that case, I know that, as you know, there is, and you mentioned that you are using an atmospheric model because you have a delay in the optical path because of the atmospheric conditions. For example, the water vapor content and also the hydrostatic balance of the atmosphere and so on. So probably this you show a curve with the two time signals, one red and one blue, of the two detectors or something like that, fitted to our straight line. And I was thinking about what is probably this shifting effect during the time. Probably it could be related to the variations in water vapor content or in atmospheric conditions or something like that. So what is the atmospheric model you are taking into account, and what is the or the atmospheric input parameters you are taking into account? Thank you.
Okay, thank you for the questions. So as for the relativistic time, I don't know, we don't take into account, but I think the overall error of our measurements are much bigger than actually the relativistic correction that would be there. Also, the meteors usually occur around 80 to 100 kilometers in the atmosphere. So for the luminous trajectory, we don't really take it into account. Only for the dark flight, where we download the MCIS atmospheric model. I think it's from the NASA. So we use that. And to get the basically pressure and temperature in the atmosphere, and well, I think that's it. And that we put it into the equations from the Zeplecha to get the Runge-Kutta integration of the whole dark flight. But for the initial luminous trajectory, we don't take the atmosphere into account in this way.
Okay, thank you for this talk. I have some questions related to AMOS astrometry. The first one is, how do you determine the beginning and the end of the trails with enough accuracy to be useful for astrometry? The second one is, what catalogs do you use for the astrometry? And finally, if you have an estimate of the average accuracy you are getting with your astrometry in terms of arc seconds.
Okay, thank you. So the as for the catalogs, actually I don't really know. I got a catalog file from my colleagues, and I matched the stars with this matched the objects with this catalog, but I didn't ask where did they get from. So it's not my computer right now, so I cannot have a look. It could be some of those catalogs, but like I said, I never asked about this, and they just gave me a file that contained the stars and their positions, and so I cannot really answer this question. Sorry.
I think the stars that they are seeing, I'm just trying to guess, are up to magnitude 6 or even less. So it's only bright star catalog most likely, I'm guessing.
That many stars there. And the other question. Well, that's the beginning and the trails. It comes from the video processing software, because they detect basically the beginning of the event and the end where the event ended. Yes. Again, I cannot really answer this question because the video processing is done by the different company. So they only give us the x and y coordinates of the beginning and each point of the on the video of the meteoroid and of the stars, and I take it from there. So then I calculate the astrometry and so on. So how do they determine the position of the beginning and of the end? It's for them. So sorry.
Okay, well, let's thank our speaker again for that very interesting talk. Thank you.